Welcome to AI Frontiers, where we explore the cutting-edge research shaping artificial intelligence. Today's episode examines 17 groundbreaking papers that dropped on December 26, 2025, revealing AI systems that learn through memory and reflection, collaborate like expert panels, and solve century-old scientific mysteries. These papers collectively demonstrate AI's next evolutionary leap toward more human-like cognitive processes. Today we embark on a comprehensive journey through AI's next evolution, examining systems that fundamentally change how artificial intelligence learns and adapts. We'll explore AI systems that learn like humans through experience rather than brute force parameter updates, understand how AI agents collaborate and deliberate to make better decisions, examine breakthrough applications accelerating scientific discovery, analyze new approaches to AI safety and evaluation that ensure trustworthy deployment, and identify the future directions that will shape the next generation of intelligent systems. The computer science artificial intelligence domain represents one of the most dynamic fields in computational science, serving as the grand laboratory where researchers attempt to crack the code of intelligence itself. This interdisciplinary field combines mathematics with psychology, neuroscience with computer science, and philosophy with engineering to develop systems that can learn, reason, and interact with complex environments. What makes this field particularly significant is its focus on building frameworks for knowledge generation and problem solving that extend far beyond academic curiosity. The current moment represents a convergence of multiple technological advances, including the maturation of large language models, integration of multimodal capabilities, sophisticated evaluation frameworks, and the emergence of truly collaborative AI systems. This convergence creates opportunities for breakthroughs that seemed impossible just years ago, with transformative potential across industries and scientific discovery. The first major theme driving AI research forward involves memory-augmented learning and adaptation, representing a fundamental shift from static, pre-trained models to dynamic systems that evolve through experience. Traditional AI systems learn during training and remain static during deployment, like students who can never update their knowledge after graduation. However, groundbreaking work like Huang's Memento 2 framework proposes theoretical foundations for continual learning through episodic memory and reflection. This approach enables AI systems to adapt through experience without traditional parameter updates during deployment, using mathematical foundations based on Markov decision processes. The revolutionary shift from static to dynamic AI systems promises agents that become smarter through daily experience, much like human learning through memory and reflection. Multi-agent systems and collective intelligence represent the second major theme, recognizing that the most challenging problems require not individual intelligence, but collective wisdom. Schneider's research demonstrates the critical importance of model diversity in AI deliberation, showing that accuracy improves significantly only when diverse models share information during decision-making processes. AI agents are now simulating venture capital decision-making processes, collaborating to solve complex scientific problems, and achieving collective wisdom that exceeds individual AI capabilities. This research challenges naive assumptions about AI collaboration, highlighting that simply having multiple agents deliberate is insufficient unless they bring genuinely different perspectives to the process. Multi-agent frameworks are solving problems that would overwhelm single systems, distributing complex tasks among specialized agents with complementary capabilities. Evaluation and trustworthiness emerges as the third critical theme, addressing the paramount need for reliable AI systems as they become more powerful and widespread. This theme encompasses probabilistic scoring frameworks for confidence-aware assessment, sophisticated detection of AI hallucinations and error patterns, and recognition of significant gaps between benchmark performance and real-world applications. Tournament-style comparisons maintain computational efficiency while providing rigorous evaluation metrics. The research reveals a critical need for robust evaluation before deployment, moving beyond impressive demonstrations to systematic assessment that humans can trust. This reflects the field's growing maturity and recognition that ensuring AI safety and reliability requires more than showcasing capabilities in controlled environments. Neuroscience-inspired architectures and domain-specific applications represent the fourth and fifth themes, drawing sophisticated insights from brain science while developing specialized frameworks for real-world deployment. Researchers are incorporating episodic memory and compositional structure into AI systems, implementing action-integrated learning that mimics human cognition, and creating specialized applications in travel planning and materials science. Domain-specific benchmarks bridge the gap between theoretical advances and practical deployment, ensuring AI breakthroughs translate into real-world benefits. These approaches aim to create more interpretable and efficient AI systems that are not just more powerful, but more human-like in their reasoning processes and energy efficiency. Among the 17 papers examined, several findings stand out as particularly significant for AI's future. Perhaps most importantly, reflection-based learning has been formalized as a mathematical process, providing rigorous foundations for AI agents that learn through experience. Research demonstrates that diversity is crucial for effective AI deliberation, with accuracy improvements occurring only when different types of models collaborate. Multi-agent frameworks have successfully solved century-old scientific mysteries, combining quantum mechanical accuracy with million-atom scalability. However, a sobering finding reveals that frontier AI models achieve only 20 to 38% accuracy when analyzing real-world biological data, highlighting significant gaps between artificial benchmarks and authentic scientific tasks. Additionally, confidence-aware AI assessment systems now maintain computational efficiency while providing mathematically rigorous uncertainty estimates. The research reveals several methodological approaches becoming standard practice in AI development, each with distinct strengths and limitations. Multi-agent frameworks distribute complex tasks among specialized agents with specific roles and capabilities, offering modularity and ability to handle multifaceted problems, though coordination can become computationally expensive. Retrieval-augmented generation with episodic memory enhances AI systems through access to external knowledge bases and past experiences, improving factual accuracy but requiring careful management of computational overhead. Probabilistic and game-theoretic uncertainty modeling provides mathematical rigor for handling complex scenarios with multiple objectives, though requiring strong assumptions about underlying distributions. Benchmark-driven evaluation enables systematic comparison of different approaches and reproducible progress metrics, though may not capture all aspects of real-world performance. Neuroscience-inspired design principles draw insights from brain science for more efficient and interpretable systems, though our incomplete understanding of brain function limits direct translation to artificial systems. Wang's Memento 2 framework stands out as perhaps the most theoretically groundbreaking work, addressing how to enable continuous learning without computational overhead and stability risks of traditional parameter updates. The core innovation lies in the stateful reflective decision process, modeling learning as two-stage interaction with episodic memory. The writing stage stores interaction outcomes corresponding to policy evaluation, while the reading stage retrieves relevant past cases corresponding to policy improvement. This elegant formulation bridges reinforcement learning theory and practical deployment constraints in mathematically rigorous yet implementable ways. Wang demonstrates that this reflective process induces an equivalent Markov decision process over augmented state memory representations, allowing application of classical dynamic programming tools. The framework uses entropy-regularized policy iteration with convergence guarantees showing that as episodic memory grows and achieves sufficient state space coverage, the resulting policy converges to optimal solutions. This provides mathematical proof that learning through reflection actually works, establishing principled foundations for memory-augmented agents in real-world deployment. Schneider's systematic investigation of deliberation effects and large language models tackles fundamental questions about collective intelligence in artificial systems. Using 202 resolved binary questions from the Metaculus forecasting tournament, researchers created 4 distinct scenarios systematically varying model diversity and information distribution. This factorial design isolates deliberation effects from other performance factors, conducting controlled experiments on AI collaboration. The key finding that deliberation improves accuracy only when diverse models share information has profound implications for AI system design. The 4% reduction in log loss achieved represents significant forecasting accuracy improvement with substantial real-world impact when aggregated across many decisions. Equally important is the negative result showing deliberation provides no benefit when homogeneous model groups engage in the same process. This challenges assumptions about AI collaboration, highlighting critical importance of diversity in collective intelligence systems and suggesting organizations should focus on assembling diverse model ensembles rather than scaling identical models. Whose Agent 2 World framework addresses one of AI planning's most challenging problems, training systems to generate accurate symbolic world models when large-scale verifiable supervision is unavailable. The three-stage pipeline demonstrates sophisticated decomposition of complex tasks into manageable components. The deep researcher agent addresses incomplete specifications by actively gathering relevant information through web search, representing significant departure from passive retrieval methods. The model developer agent implements core generation capability, translating natural language specifications into executable world models. The testing team represents perhaps the most innovative component, conducting adaptive unit testing and simulation-based validation that provides behavior-aware feedback beyond syntactic checking. The adaptive testing discovers edge cases and failure modes missed by predetermined test suites, essentially creating AI systems that can debug themselves. Experimental results demonstrate consistent state-of-the-art performance across multiple benchmarks, with 30.95% average relative improvement from fine-tuning on multi-turn trajectories, showing the framework serves effectively as both inference time solution and data generation engine. Looking toward the future, several key challenges emerge that will shape AI development's next phase. Scalability of memory-augmented systems remains uncertain as episodic memory volumes grow large, raising questions about whether systems can function effectively while remembering every detail of every experience. Computational overhead of multi-agent deliberation and complex evaluation frameworks could limit practical deployment, requiring continued optimization and efficiency improvements. The diversity requirement for effective AI collaboration poses technical and practical challenges, as creating genuinely diverse model ensembles while maintaining coherent system behavior requires design and coordination mechanisms not yet fully understood. Most importantly, the field must develop robust evaluation methods assessing AI capabilities across full spectrums of real-world deployment scenarios. Current benchmarks may not capture all practical performance aspects, potentially leading to systems excelling in evaluation but struggling in deployment. The future appears to move toward more integrated, adaptive, and collaborative systems that can reason, learn, and interact in complex environments while maintaining safety and interpretability necessary for widespread deployment. 4 key takeaways emerge that will likely define AI research trajectory in coming years. First, the shift from static pre-trained models to dynamic memory-augmented systems represents fundamental evolution in AI deployment thinking. Second, diversity's critical importance in AI collaboration highlights that artificial intelligence's future involves creating effective ensembles leveraging different perspectives rather than just building more powerful individual models. Third, the gap between artificial benchmark performance and real-world scientific task performance reminds us of substantial remaining work in making AI truly useful for complex authentic applications. Finally, integration of neuroscience insights, sophisticated evaluation frameworks, and domain-specific applications suggests AI's future will be characterized by carefully designed systems tailored to specific contexts while maintaining broad applicability and robust performance standards. These papers provide a roadmap for this evolution, highlighting tremendous potential and significant challenges ahead. As we conclude today's exploration of these groundbreaking papers, the research provides clear direction for AI's continued evolution. Progress requires not just technological innovation, but careful attention to evaluation, safety, and fundamental principles guiding intelligent behavior. The convergence of memory-augmented learning, collective intelligence, and neuroscience-inspired architectures points toward a future where AI systems truly augment human capabilities while maintaining trustworthiness and interpretability. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv preprint server.